So here we're now back into the study of probability through probability distributions. Okay, so up until the last time we did probability in our course, we looked at the probability of individual outcomes of events. Now in this part of the course, we're going to look at models for the distribution of the probabilities of all possible outcomes that have all equal likelihoods. Okay, so before we do this, we need to define a couple of things, or terminology here. So we're going to look at random variables. So a variable, they can have any value within a range. We're going to use this capital letter X to denote the random variable, while we're going to use the lowercase x to represent all the possible outcomes of the random variable x. Okay, so this one's capital, and this one is lowercase. Now, if the random variable is a number rolled with a die, as an example, then the x will have a different value for each of the 6 possible outcomes. Okay, so that would mean, like, capital X could be 1, 2, 3, 4, 5, 6, and the little lowercase x would represent the value for each outcome. Okay. Then we have discrete variables. So these are the variables that have only a finite and distinct values within a range. So example, the number of phone calls made by a salesperson must be an integer. You can't have 5.2 phone calls. Continuous variables are the variables that take on all real infinite values within a range. This is the one where you can take into account all kinds of rational numbers and decimals, etc. So example, the length of time one spends on their cell phone, since it can be measured as fractions of a second. Now we're going to be spending a lot of time looking at probability distributions. Okay, so this is a function that gives us the probability of all possible values of a random variable, and is denoted by the capital P, and our input would be the random variable x equal to some the number of possible outcomes, or the lowercase x, the possible outcomes of the random variable. Okay. Or in short form, we'll just say P of x. An accompanying probability distributions would be the probability histogram. So it's just a graph of a probability distribution, which equal intervals are marked on the horizontal axis, and the probabilities associated with these intervals are indicated by the areas of the bars. So we're going to use histograms really to give us a visual way of looking at a probability distribution. So let's look at example 1. Okay, the table gives a percent breakdown of the number of rooms in apartments in a particular complex. So the random variable is x, and it's denoting the number of rooms. So as it says up here, we're looking at the random variable. Okay, so the random variable is x, the number of rooms, and we can have 2, 3, 4, 5, or 6 rooms. Now the probability of having 2 rooms is 15. Probability of having 3 rooms is 30. 4 and 42, 5 and 10, and 6 and there's 3. Okay, so kind of the associated number of outcomes of getting 2 rooms, 3 rooms, 4 rooms, 5 rooms, and 6 rooms. Okay. So let's identify the random variable here. It is going to be the number of rooms in an apartment. So the number of rooms in an apartment. And we're going to construct a probability histogram because we're given the probability of values here. Okay, so the probability, P of x, and number of rooms in the bottom, x. So looking at the first one, 2. So the first one is 15. So we're going to graph here. What we're graphing here is the probability of x versus x. Okay, now how can we do this? Now, when you think for a moment, how would we look at probability? Remember, probability is a value between 0 and 1. And my y-axis scale here, I only got to 0.5 because nothing exceeds 50%. But if you look at the table of values, okay, what did these all add up to? These all add up to 100. If you add all of these 5 values up, they all total 100%, right? Because these are probability values, right? So they have to all add up to 100%. All of your possible outcomes all add up to 100%. Okay, so when you talk about 15, we're talking about 15% on a scale where you're going from 0 to 1. 15% is going to represent 0.5 or 0.15. So for 2 rooms, I'm going to go to 0.15. Now, I'm drawing a histogram here, so I have to represent this by bars. So I'm going to represent this by drawing a bar to 0.15. And it's centered around 2 because its number of rooms is 2. So there's my first bar. So maybe I can just use a ruler. Let's see if I can use a ruler for this. Or we'll draw a rectangle. So we draw, yeah, good. We can draw a rectangle. Here's a rectangle. Just like that. So there's our first rectangle. Now the second one is 30, probability of 30. 30 to get 3 rooms. Okay, so I'm going to draw a rectangle to 0.3. And again, it's centered around that interval of 3. Just trying to, you should try to make your bars as even as possible. So we should make this one a bit wider. There we go. And then for 4 rooms, I have 42, so 0.42. I'm going to try and get it as best as possible to that value. And then I'm trying to make the bars look even. Okay. And then we have for 5 rooms 10%, so we're going to draw a bar all the way to 0.1, centered around 5 rooms. And then for the last one, for 6 rooms, we have a 3% chance, which would represent 0.03 on my histogram here, which is very small. Again, you just kind of approximate there. So there we go. So there's my histogram. It's maybe shaded in a little bit. And just draw a few shaded lines like this. And as a rough way to draw a histogram. If you're using computer software to do these things, then probably you can make it look a lot nicer. But there's roughly what our histogram is going to look like. So you can see the distribution of probabilities visually, and you can see the highest probabilities getting 4 rooms because it has the highest bar. Okay. So explain the meaning of the individual bars and histograms. So the area of each bar represents the probability. So the area of each bar represents its probability. Okay, and this probability is shown on the vertical axis. Part D, describe the distribution. So we can say 4-room apartments occur most frequently. 4-room apartments occur most frequently. Okay, it just so happens like we're looking at frequency and probability as being the same thing in this kind of a problem, right? Just imagine there's 100 rooms in this complex. Well, 42 rooms would 42 apartments would have 4 rooms in them, right? So, but it just speaks by looking at this as a probability problem too. Like it's the same thing as saying 42% of the rooms are 42% of the apartments are 4 rooms. So 4-room apartments occur most frequently. The probability to decreases if the number of room increases or decreases from 4. So the probability decreases as the number of rooms increases or decreases from 4. Okay, part C, calculate the sum of the probabilities. Does this confirm the results in the sample? And if you add up all the probabilities, the sum of all probabilities is 1, or you could say 100%. And so this confirms the result in our example. All right, let's go to example number 2, the expectation of a probability distribution. So let's make a tree diagram to show the probability distribution for the number of girls in a family of 3 kids. So if you decide to have kids, let's draw a tree diagram here. And you're going to draw the first branches of your tree. And when you have a kid, for the sake of simplicity and argument here, you're just going to say boy or girl. So let's say you can have a girl here or a boy here, and you have a 1/2 chance for a boy, 1/2 chance for a girl. Okay? That's for your first kid. For your second kid, continue drawing some of these branches here. So you can have, again, another girl or boy. If you have your first child is a girl, you can have another girl or boy. If your first child is a boy, you can also have you can have a girl or another boy. Okay? And each of these outcomes at this step is half or 50%. Okay? And then your third child, again, continue extending your branches. Another girl, boy, another girl, boy, and girl, boy. And this third child's level, each of these outcomes, 50% having a boy or having a girl as you follow the branch. Okay, so there's a little tree. Okay, and you don't necessarily have to put these half fractions here; just trees sufficient. Okay, I'm just going to fill in the table here to help us calculate all these probabilities. So number of girls is x. That's our variable. So we have 0, 1, 2, or 3 in a family of 3. Okay, so what's the distribution of girls when you have no girls? Well, this means you have all 3 boys, right? So boy, boy, boy. Meaning you're following down this branch of the tree. Boy, boy to boy. Okay? Frequency, well, that only happens once. You can only have one outcome where you have all 3 boys. So the probability is going to be 1 out of 8. Why 8? Because if you count the end of the branch, each of these branches, you have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So you have boy, 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 girl, boy, girl, boy, 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 girl, 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 boy, boy, girl, 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 boy, and girl, girl, girl. So you have all 8 different branches to follow from the root of your tree all the way to the end. So what if you have one girl here, continuing our table? So one girl here means you could have, the arrangements are boy, boy, girl, boy, girl, boy, and girl, boy, boy. Okay, so there's 3 different ways you can get that to happen. So the probability is 3 out of 8. What if you had 2 girls? Well, you could have girl, girl, boy. You could have girl, boy, girl. And you could have boy, girl, girl. For a total number of 3 outcomes. So again, another 3 out of 8. And finally, number of girls, we get all 3 girls. Well, there's only one way to get all 3 girls. Is if every girl is boy and a girl. There's one outcome, one frequency for that. So 1 out of 8. And if you add them all up, 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8, add up to 8 out of 8, which is 100%. So let's make a probability histogram for this distribution. My probability, I'm going to use eighths just to make life simple. So here we have 1/8, and up here I'll have 3/8, and my last tick mark here will be 5/8, counting by 1/8 as we go up. Okay, I only need to go up to 5/8. There's nothing you need to you only go up to 3/8. So I don't need to go any higher than that. So yeah. All right, so let's do number of girls. You can have 0, 1, 2, or 3 girls. And I'm going to draw my histogram. So we have to draw some bars here. So for 0 girls, it's a frequency of 1/8. So you draw a bar for up to 1/8. Make sure your bar is centered around your 0 there. And we continue on. My 1 girl outcome is going to be 3/8. So again, I draw another bar to represent that. And try to make them even as possible. And over here as well. Okay, and we're just going to copy that and paste it. Let's see. Nope. All the way down here. Let's bring it back up. And paste it like that. So again, another 3/8 for 2 girl outcomes. And then finally for the outcome with all 3 girls, another 1/8. So we can just draw that last bar like that. Okay. So it's a distribution. It looks somewhat symmetrical. It's symmetrical about between 1 and 2. Okay. And that's it. That's our probability distribution. All right. So parts to calculate the weighted mean number of girls in a typical family of 3 children. So the weighted mean number, because each number of girls has a different weight in terms of probability assigned to each of it. So remember our formula for the weighted mean, it's x bar, W for weighted, it's equal to sigma of XW, the sum of all the individual weights divided by the total number of weights, right? So in this case, weights are our outcomes. So if we have 0 children as our data point, then we have probability of 1 doing that. Or, if there's one outcome, it's a weight of 1. And if we have 1 girl, then we have three outcomes for that. So 1 times 3 plus 2 girls, again, 3 outcomes for that, so 2 times 3. And for 3 girls, is 1 outcome for that, so 3 times 1. Divide that by the total number of outcomes, 8. So in this case, weight is like total number of outcomes, or the number of outcomes, because it's giving us the weight of each value. Okay, so altogether we have 3 plus 6 plus 3 divided by 8, which is 12 over 8, or 1.5. So the mean value, the average value, the mean average is 1.5 girls per family with 3 children. Part D, calculate the expectation for the number of girls in a family of 3 children and compare it to the mean. So what is the expectation? So the expectation or expected value is a very important concept here. It's a function E with the input of x. So this is not like E times x, it's just saying the function E, like the function f. We studied functions in grade 11, so E is the function, x is the input. So this is the predicted average of all possible outcomes of an event, and the expectation is equal to the sum of the products of each outcome, x, with its probability p of x. Okay, so we take every single outcome and multiply it by its probability and add them all up. Okay, so the expected value E is equal to the sum of all outcomes times the probability of each outcome, which is equal to the x1 p1 plus x2 p of x2 plus dot 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 all the way to the last outcome at xn times p of xn. I should say p of x1 over here. Okay, so this is kind of like a general formula, general rule for expected value. So in our particular example, let's look at our outcomes. We have 0 outcomes, so 1 girl, 0 girls, 1 girl, 2 girls, or 3 girls. And I multiply each of these outcomes by its probability. So 1 out of 8 plus 1 times 3 out of 8 plus 2 times 3 out of 8 plus 3 times 1 out of 8. Okay, and so if I multiply all those together, so 0, then add 3 out of 8, then add 6 out of 8, and then add 3 out of 8. Add up all these fractions together, I get, again, 12 over 8, which is 1.5. So the weighted mean and the expected value are the same. Okay, so the weighted mean and expected value are the same. Okay, so let's interpret the results. On average, a family of 3 kids would expect to have 1.5 girls. So on average, a family of 3 kids would expect to have 1.5 girls. Now, in this kind of a context, it's hard to make sense of 1.5 of a human being, but mathematically, that's what we're saying. Each family of 3 kids would just have 1.5 girls. Let's look at another example of expected value. So a hospital is having a fundraising lottery to raise money for cancer research. A ticket costs $10 and 2 million tickets are available. There are 4 levels of prizes: a $5 million grand prize, 3 $100,000 second prizes, 10 $1,000 prizes, and 2,000 free tickets for next year's lottery. What are the expected earnings per ticket? So let's look at one method of doing this called let's use the weighted mean. So method 1, weighted mean. Okay, so the expected value, Ex, is equal to the total value of all prizes divided by the number of tickets sold. Number of tickets sold. Okay, so what are the outcomes? Well, you have one $5 million prize. We'll add to that three $100,000 prizes. Plus, we'll add to that 10 $1,000 prizes. Plus, we'll add to that 2,000 uh, 2,000 free tickets, which cost $10 each. So 2,000 times 10. Okay, and we divide that by the 2 million tickets that are sold. All right. So the numerator part, when I do all that math, I get 5,330,000. And divide that by 2 million. So the value here, the weighted mean, the expected value is 2.665. So in other words, if this calculation is about dollars, right, ticket costs and prize earnings, the expected value per ticket, because this is the total value divided by ticket, so the value that you win per ticket is this division, it's $2.66. $2 you'd expect to win $2.66 out of every ticket. That's the expected value. It's like you're assigning value to each ticket. Okay, another way of looking at it is, so method number 2, using expected value. So e to the x is equal to the outcomes times the probability of each outcome. Okay, so you have one outcome of 5 million. The probability of getting the $5 million ticket is 1 out of the 2 million tickets. Okay, what about the $100,000 prize? Well, there's 3 of those prizes, so you have 3 out of 2 million to get a chance to win that. Plus, well, you have the $1,000 prize, and there are 10 of those, so 10 out of 2 million. Plus 10 the free tickets, so each value of the free tickets is $10, so you have 2,000 free tickets, so 2,000 out of 3 million. Okay, and then when you do that, when you add up these numbers together, you get the same result. So it's just you can factor out 1 out of 2 million, so 1 over 2m, and you just add up the individual prize amounts. So 5 million plus 300,000 plus 10,000 plus 20,000. Oh, sorry, 2,000. Right, 2,000. No, 20,000. Multiply the 10. Okay. I just should 2 of them. Okay, and then you're going to get the same results, 2.665. So I'd say here, therefore, each ticket is expected to win $2.66. Okay. So part B, what is the expected value of the ticket and what does it mean? So we're going to say here, since each ticket costs $10, the expected value of each ticket is, well, $2.65. That's your prize winning, but you spent $10 in the ticket. So what you end up having is a loss of $7.33 or 34 cents. Okay, so on average, this is all average. Expected values are averages. So on average, each ticket is worth a loss of $7.33. So this is what the problem with lotteries is. People don't realize every time you buy a ticket, you lose money on average. On average, like, there's a lucky few winners, but on average you lose. Otherwise, because if you won, if you spent $10 and you automatically get $20 of expected value winnings, then the lottery wouldn't make any money. So expected value is a loss. Okay. So example 4: a committee of 4 is to be chosen randomly from 4 males and 6 females. what is the expected number of females on the committee? So the expected value, E of x, is equal to the sum of all outcomes times the probability of each outcome. Okay, so a committee of 4. So I need to know expected number of females. So if I have 0 females times the probability of 0, so 0 times probability of 0, plus 1 female times the probability of 1 female, plus 2 females times the probability of 2 females, and plus 3 times the probability of 3 females, plus 4 females times the probability of 4 females. Okay, and so let's calculate that. Remember counting? Choosing randomly from 4 males and 6 females. Okay, does order matter? No, it does not. Okay, it's not like we're choosing certain positions like president or secretary. The order does not matter. So for 0 females, you're going to choose, so you're looking at the probability of choosing 4 males from 4. There's 4 males there, so 4 males from 4. And there are 10 people in total, so 4 plus 6 is 10. So here we have 10 choosing 4. So that's the total number of ways you can choose your people for your committee. And so on the top is how many ways you can choose 4 males from 4 males, divided by the number of ways you can choose 4 people from 10 people. Okay, that's your probability. Okay, plus if you want 1 female in your committee, probability of getting 1 female, well, it's there's 6 females to choose from. So it's 6 choose 1 times 4 choose 3. You're still going to choose 3 males if you chose 1 female. And the total number of outcomes, so 10 choose 4. Okay, plus 2 females, so it's going to be 6 choose 2 times 4 choose 2 for the males, and then 10 choose 4 in total. Plus, if you want 3 females, the probability of choosing 3 females is 6 females choose 3, and 4 males, choose 1 to make a committee of 4, and then your total 10 choose 4. And then finally for 4 females, it's going to be 6 choose 4 times 4 choose 0, because you're not choosing any males anymore, and 10 choose 4. Okay, and then I kind of simplify a lot of this, so 0 plus 1 female, and the outcomes here are 24 out of 210, plus 2 females here, and so the probability is 90 out of 210, and 3 females, and the probability is 80 out of 210, and then we have 4 females, and the probability is 50 out of 210. Okay, and if we calculate that, add them all up, we get 504 out of 210, which is equal to 2.4. So the expected value is 2.4 females to be selected for the committee. So therefore, you would expect 2.4 females to be selected for the committee. Okay, and that ends 4.1.